Hi everyone. In the last lecture, we have discussed the spectral measure and have seen a few examples and some important properties of the spectral measure. So, if x omega mu is a measure space and h is a Hilbert space, a spectral measure for x, omega, and h is a map E from omega into B of h satisfying the following condition that E delta is an orthogonal position for each delta in omega, and E sends phi into 0, empty set into the 0, and E of x is the identity. E of delta 1 delta 2 is E of delta 1 into E of delta 2, and if delta j is a sequence of pairwise disjoint sets from omega, then E of union delta n is nothing but summation n equal to 1 to infinity E of delta n. And we have seen that the convergence on the right hand side of the equation star is with respect to the strong operator topology of P of h. So we have seen few examples, and this is one of the important property. If we fix two vectors g and h from Hilbert space h, and if E is a spectral measure, then if we define E suffix g at delta is inner product E delta g with h, this gives a complex measure with total variation at most norm g into norm h. And using this, we were able to discuss the integral of phi with respect to the spectral measure. If E is a spectral measure for x omega h and phi is a bounded measurable function, then we have shown that there exists a unique bounded operator A on h with the following property that given any epsilon positive and delta 1, delta 2, so on delta n, a partition of x with the property that supreme of mod phi x minus phi y, where xy in delta k is less than epsilon. So this is known as the oscillation of the function in delta k. If this is less than epsilon, then for any choice of elements xk in delta k, norm of A minus summation k equal to 1 to n phi of xk E delta k is less than epsilon. Okay, so now once we get this result, we were able to define A as integral phi dE, or in other words, inner product Ag with h is nothing but integral over x phi x d of gh x. And from this we can also find out what is the adjoint. So we can also show that A star g h is integration over x phi of x bar d of E g h x. This directly comes from uh, this result, that approximation of AGH with these functions summation k equal to 1 to n phi of xk inner product E delta k g with h. Now using the definition of the adjoint of A, we can actually show that A star is given by this relation. Now let us look at set of all bounded measurable functions. Let us denote B of x omega to be set of all x f from x to c. F is bounded and omega measurable. So if you define subnorm on this space, so this is a Banach space, and if you define f star of x as f of x bar, this is an involution, and with respect to this involution and subnorm, this is a Banach, this is a C star algebra. So B of x omega is a C star algebra. Now we want to show that given any spectral measure on x omega h, we can get a representation on B of x omega. Okay, so today we are going to discuss about spectral measures and representations. Let E be a spectral measure on x omega h, then the map rho from b of x omega into b of h defined by rho of phi is integration over x phi dE this is a representation and rho of phi is normal for all phi in b of x omega. Okay, that means given any spectral measure on x omega h, we can get a representation using the spectral measure. Okay, so let us look at the proof. So by the earlier observation, we can easily look at what is rho phi star, that is integration over x phi bar dE. That is easy to look at. Rho phi star is nothing but rho of phi bar, and in fact we can also show that rho of phi is normal for every phi in b of x omega. So to prove this is a representation, we only look at the multiplicativity property of rho. So we will show that rho is multiplicative. So let us take phi and psi from b of x omega. Let epsilon be positive and delta 1, delta 2, delta n be a partition of so let us take omega equal to phi psi or phi psi, the product of phi and psi. Then for each xk in delta k, so assume that supreme of mod omega x minus omega y, where xy is coming from delta k, this is less than epsilon for all k equal to 1 to so on n. Then by the earlier result, then for each xk in delta k, we have the following, that is integral over omega d minus summation k equal to 1 to n omega xk into e delta k. This norm is less than epsilon. So let us call this inequality to be 1. This follows from the earlier result. Okay. Now we want to show that, so the claim is the following: norm of integral phi psi d minus integral phi d integral psi d is less than epsilon. From that we can conclude that integral phi psi d is nothing but integral phi d into integral psi d, that is this map is multiplicative. Okay, so let us look at this part. So let us consider norm of integral over x phi psi dE minus integral over phi dE into integral over psi dE. This is by triangle inequality integral over less than or equal to integral over x phi psi dE minus summation k equal to 1 to n phi of xk psi of xk e of delta k plus norm of summation k equal to 1 to n phi of xk psi of xk e of delta k. So we are adding the term summation k equal to 1 to n phi of xk psi of xk into e of delta k, adding and subtracting. And now here we are adding summation k equal to 1 to n phi of xk e delta k into integration over psi dE plus integral summation k equal to 1 to n phi of xk e of delta k into integration over psi dE minus integral over x phi dE integral over x psi dE. Okay, now we know that the first term is less than epsilon by the property of omega by inequality 1. So this is less than epsilon, and the second term we can actually show that if you look at, you can take summation k equal to 1 to n phi of xk e of delta k into summation k equal to 1 to n psi of xk e of delta k minus integral over x psi dE. This is because delta 1, delta 2, so on, delta k, delta n is a partition for x, and e delta since delta k's are disjoint, so e delta k into e delta j is nothing but 0. Now using that we can get this, and the last term you will get summation k equal to 1 to n phi of xk e of delta k minus integration over x phi dE into norm of integral over x psi dE. The last term you will get this one. Okay, so this is less than, the first term is less than epsilon, and the second term, so less than or equal to this term into this term. The second term is less than epsilon, the first term is less than or equal to subnorm of phi, so this is epsilon into norm of phi, and here the last term, so in the last term the first factor is less than epsilon and the second factor is less than subnorm of phi, so this is nothing but epsilon into 1 plus norm phi subnorm of phi plus subnorm of psi. Now this is true for every epsilon, hence we can conclude that integration over x phi psi dE equal to integral over x phi dE into integral over x psi dE. That means we can say that rho of phi psi is rho phi into rho psi. So the other part, that rho phi is normal, follows from the definition of rho phi star that we have already discussed. So this completes the proof of the result. So this result says that given any spectral measure, we can get a representation from B of x omega into B of h. Now we can ask the question, what will happen to the converse? In particular, we can say that spectral measure E defines a representation on C of x, because C of x is a subset of B of x omega. Okay, that means given any spectral measure, we can get a representation. Now we want to look at the converse question. So before looking at the converse part, let us fix these two notations. If x is a compact space, then B of x denotes set of all functions from x into C, where f is bounded and Borel, and mx denote the space of all complex regular Borel measures defined on x. So we need the following lemma: if x is a compact space and phi is a map from x into C, which is bounded and Borel, then there is a net of continuous functions defined on x such that the subnorm of ui less than or equal to subnorm of phi for every I in lambda, where lambda is a directed set here, and integral over x ui d mu converges to integral over x phi d mu for every mu in mx. So using this result, we want to prove our main theorem. If x is a compact space and rho is a map from C of x into B of h, which is a representation, then there exists a unique spectral measure E defined on the Borel subsets of x, such that for every gh in h, E suffix gh is a regular complex valued Borel measure, and not only that, rho of u is nothing but integral over x u dE for every u in C of x. Earlier we have shown that given a spectral measure E, if you define rho of u as integral over x u dE, that gives a representation. Now we are looking at the converse part. That means if given a representation from C of x into B of h, we want to represent it by a spectral measure. Okay, the idea of the proof is that we want to use the Rees-Markov theorem to get a measure, and using that measure we want to define spectral measure. So to do that, let us fix two elements g and h in h, define lambda from C of x into C by lambda of u equal to inner product rho u at g with h for every u in C of x. We can show that lambda is bounded and it's also linear, and norm of lambda is less than or equal to norm g into norm h. So this is a bounded linear functional defined on C of x, hence by the Rees-Markov theorem, there exists a unique measure which we denote by mu gh, because it depends on g and h as lambda depends on g and h, such that lambda u is nothing but integral over x u d mu gh for every u in C of x. Now if you write down what is lambda u, we know that lambda u is nothing but inner product rho u at g with h. So if you write down this one, we will get inner product rho u at g with h is nothing but integral over x u d mu gh for every u in C of x. So let us call this equation by 1. Okay, next we want to show that this representation can be extended to the space of all bounded Borel measurable functions. So to do that, let us look at phi in B of x and define B of gh equals to integral over x phi d mu gh for every gh in h. Now using the property of mu gh, we can actually show that B is a sesquilinear form and it is also bounded by subnorm of phi. Hence there exists a boundary linear operator. Let us say it is A from h to h, such that B of gh is nothing but inner product Ag with h. Since B depends on the function, so let us write down the operator by rho tilde phi instead of operator A. So we can write get that inner product of rho tilde phi acting on G with h is nothing but integral over x phi d mu gh for every gh in h. So let us call this equation 2. So if we observe equation 2 and equation 1, there is only one difference, that is equation 1 is valid for a set of all continuous functions, whereas equation 2 is valid for all phi in B of x, set of all Borel functions, bounded Borel functions defined on x. So that means when we take u in C of x, then rho tilde phi and rho tilde of u and rho of u both coincide. That means we have extended the representation rho u from continuous functions into bounded Borel functions. Okay, so we want to claim that rho tilde, which is a map from B of x into B of h, this is a representation, and as we have already observed, rho tilde and rho coincides on the space of all continuous functions. Now we want to show that rho tilde is multiplicative. So let us take phi in B of x. Then by applying the earlier lemma, by this lemma we can get a net of continuous function ui whose norm is less than or equal to norm of phi, and integral over ui d mu converges to integral over phi d mu, integral of phi d mu for every mu in mx. So if we apply this result, we can actually get a net of continuous function ui with this property, which is given by 3, that is integral over x ui d mu converges to integral over x phi d mu for every mu in mx. This is true for any measure. Now if psi is in B of x, we want to show that rho tilde of phi psi equal to rho tilde phi into rho tilde psi. So for that purpose, let us take one more element psi in B of x. Then we can treat psi into mu as a measure in the usual way, that is if you look at E going to integral over E psi d mu, that gives a measure. Now using that and lemma again, we can actually conclude that integral over x ui psi mu converges to psi d mu converges to integral over x phi psi d mu for every mu in mx. Again this is true for all measures mu in mx. Okay, now if you look at equation 2, so this is nothing but rho tilde phi g rho tilde phi at g with inner product with h is the integral over x phi d mu gh, and here we got integral ui psi d mu converges to integral over phi psi d mu. Now if you take vector g and h, and if you look at rho tilde ui psi acting on g with inner product h, that converges to integral over rho tilde phi psi g acting on h for every g and h. So that is because of equation 2. Okay. That means we can conclude that rho tilde ui psi converges to rho tilde phi psi in the weak operator topology of B of h. So let us call this as star. So in particular, if you take psi in C of x, let us look at, so we already took phi from B of x, and in particular if psi is in C of x, we want to say that rho tilde phi psi is nothing but limit I rho tilde of ui psi, that is limit I rho of ui psi, because ui's are continuous and psi is also continuous, the product is continuous. So rho tilde and rho are same on the continuous functions. So that can be written as limit over I rho of ui into rho of psi, because rho is a representation on C of x. Now we know that rho ui converges to rho tilde of psi, and we can write down rho psi as it is. Now rho psi can be written as rho tilde of psi, because rho and rho tilde are same on the space of all continuous functions. So what we have shown was rho tilde of phi psi is nothing but rho tilde of phi into rho tilde of psi, where phi is coming from b of x and psi is coming from c of x. Okay, now if psi is coming from b of x, then we have to show the same identity holds true, same equality holds true. So let us take psi from b of x, that is psi is a bounded Borel function. Then we have rho tilde of ui psi is nothing but rho of ui into rho tilde of psi, because of the earlier observation. Now this converges to rho tilde of phi into rho tilde of psi, because rho of ui converges to rho tilde of psi in weak operator topology. Hence we can say that by the earlier so we know that rho tilde of ui psi converges to rho tilde of phi psi by star in the weak operator topology, but here we got that rho tilde of ui psi converges to rho tilde psi into rho tilde of phi, which is given in star. So this is also convergence in the weak operator topology. Hence by star and double star, the same rho tilde of ui psi converges to rho tilde of phi psi, whereas in the double star it converges to rho tilde of phi into rho tilde of psi. So since the limit of these operators is unique, we can conclude that rho tilde of psi into phi is nothing but rho tilde of psi into rho tilde of phi. That means rho tilde is multiplicative. Now the other part of other properties of rho tilde can be obtained in a easy way. Apart from this, remaining are easy properties to be verified. So next we want to define a spectral measure using rho tilde. So far we have defined, we got a measure mu gh, and using the fact that rho is a representation, we extended that representation to rho tilde from b of x into b of h, and we have shown that it is multiplicative. Next we want to define spectral measure using rho tilde. So if delta is a Borel subset of x, we can actually define E of delta to be rho tilde of chi delta. Now if you take delta to be empty set, then chi empty set, chi of delta is nothing but 0, hence rho tilde of 0 is 0, so we can get E of empty set is 0. E of x is rho tilde of chi of x, so that is a constant function rho tilde 1. If you look at equation 2, by 2 rho tilde of 1 g inner product with h is nothing but integral over 1 d mu gh, so that is nothing but rho tilde of 1 gh is nothing but integral over x d mu gh, but that is nothing but again we can express in terms of lambda of 1. So by 2 rho tilde of 1 g inner product with h is integral over x 1 d mu gh, that is mu gh of x, and this is, if you look at the definition of lambda, that is given in terms of mu gh. So lambda 1, so lambda of 1 is integral over x d mu gh. So from that we can actually show that mu gh at x is nothing but inner product lambda 1 acting on g with h, but we know that lambda 1 is lambda 1 at g is g, so we get inner product g with h. So from this we can say that rho tilde 1 is nothing but the identity operator on the Hilbert space H. So next let us take delta 1 delta 2 measurable subsets. Then E of delta 1 intersection delta 2 is by definition rho tilde of chi of delta 1 intersection delta 2, and we know that chi of delta 1 intersection delta 2 is nothing but chi delta 1 into chi delta 2. So if you write that, you will get rho tilde of chi delta 1 into chi delta 2. We know that rho tilde is a multiplicative map, so that is nothing but rho tilde of chi delta 1 into rho tilde of chi delta 2. And by definition of E of delta, we can actually conclude that this is nothing but E delta 1 into E delta 2. So we have shown that E of delta 1 intersection delta 2 is nothing but E delta 1 into E delta 2. Now let us take a sequence of disjoint Borel sets, pairwise disjoint Borel sets, delta n. So let us write delta to be union delta n equal to 1 to infinity, and lambda n equals to union delta k equal to n plus 1 to infinity. Now using the linearity of rho tilde, we can actually show that E is finitely additive. For example, if you take delta 1 intersection delta 2 is empty, then E of delta 1 union delta 2 by definition, that is rho tilde of chi of delta 1 union delta 2, but chi of delta 1 union delta 2 is nothing but chi of delta 1 plus chi of delta 2. Now using the fact that rho tilde is linear, that is rho tilde of chi of delta 1 plus rho tilde of chi of delta 2. From that we can actually show that E delta is nothing but E delta 1 plus E delta 2. So now that can be applied for finitely many disjoint sets. So now we want to show that E delta is nothing but limit of summation k equal to 1 to n E delta k h as n going to infinity. So let us take h in h. So look at norm of E delta h minus summation k equal to 1 to n E delta k h square. So that can be written as inner product E lambda n h with itself. Now E lambda n is a orthogonal projection, so that is self adjoint and it's also idempotent. Now using that fact, we can say that this is equal to inner product E lambda n h with h. But by definition of E delta, so this is nothing but inner product rho tilde of the characteristic function supported by lambda n acting on h with inner product with h. So this is nothing but by definition of rho tilde integral over x chi of lambda n d mu hh. So again by the definition of measure, this is mu of hh acting on lambda n. Now we know that mu of hh is a measure, so from this we can conclude that mu of hh acting on lambda n converges to 0 as n going to infinity, because lambda n is nothing but union delta k equal to n plus 1 to infinity. Okay, so what we have shown is E delta h, that means E of union delta n equal to 1 to infinity acting on h is nothing but summation n equal to 1 to infinity E of delta n acting on h, and this is true for every h in h. That means the series converges to the left hand side in the strong operator topology of B of h. So we can conclude that E is a spectral measure. Okay. Now next we want to show that rho tilde of phi is nothing but integral over x phi d mu. Okay. So let us take phi in B of x and epsilon positive, and let delta 1, delta 2, so on, delta n be a partition of x such that its oscillation in delta k is fine less than epsilon, that is supremum of mod phi x minus phi y, where xy is in delta k is less than epsilon for all k equal to 1 to so on n. Now if xk is in delta k, so by looking at the oscillation in the set delta k, so we can conclude that norm of phi minus summation k equal to 1 to n phi of xk chi of delta k subnorm is less than epsilon. Now if you look at norm of rho tilde phi minus summation k equal to 1 to n phi of xk rho of chi delta k, that is E delta k, that is less than or equal to norm of rho tilde into norm of phi minus summation k equal to 1 to n phi of xk into chi of delta k. We know that rho tilde is contraction, so that is less than or equal to 1, hence by the above equation, by the above inequality, we can actually conclude that norm of rho tilde minus summation k equal to 1 to n phi of x k e of delta k less than epsilon. So by definition, this is nothing but rho tilde of phi is nothing but integral over x phi dE. So in particular, when u is a continuous function, we know that rho tilde at u equal to rho of u, that is integral over x u dE for every u in C of x. So here what we have shown is that if you have a representation rho from C of x into B of h, we got a unique spectral measure E satisfying rho of u is nothing but integral over x u dE, and in fact we can show that the spectral measure satisfying this condition is unique. That can be shown in a easy way. So let me quickly revise the steps that we proved in this result. So we are given with a representation from C of x into B of h. Now fixing two elements g and h, and defining a functional like this, lambda from C of x into C by lambda of u equal to inner product rho u at g with h for every u in C of x. This gives a bounded linear functional. Now we can apply the Rees-Markov theorem to get a measure which depends on g and h, that is mu of gh. Now once we represent lambda u with respect to this measure, we have extended this to set of all bounded Borel functions in this way, and using this integral over x phi d mu gh, we got a bounded sesquilinear form, and because of this we got a bounded linear operator which we have denoted by rho tilde phi, which is given by equation 2. And we have, from this actually we can conclude that rho tilde coincide with rho on set of all continuous functions. Then we have shown that rho tilde is multiplicative by using the earlier lemma that we have stated. So first we have taken one function from B of x and other function from C of x, and we have shown that rho tilde is multiplicative, and later we use this lemma again to get that rho tilde is multiplicative when we take two functions from B of x. Okay. Then we have defined the spectral measure using rho tilde in this way. E of delta is nothing but rho tilde of chi delta, and using the representation of rho tilde, we were able to show that E gives a spectral measure. And then we wanted to show that the representation that we have started with is is associated with the spectral measure in the following way, that is rho of u is nothing but integral over x u dE for every u in C of x. So this completes the proof of the result. I'll stop here. Thank you very much.